Okay, so this video is the last or the third video for section 4.3. It's dealing with just page 4. We're still dealing with the idea of growth and decay. In this case, we're sort of going to be talking, it's going to be working more as a decay, and we'll talk about what I mean by that in a minute. So Newton's law of heating and cooling. All right, so Newton discovered that an object is going to cool at a rate that is proportional to the difference between the object's temperature and the ambient temperature. So let's say, for example, I have a cup of coffee, and the temperature of that coffee is, let's say, 200 degrees Fahrenheit. All right, no, and I pour the cup of coffee, and then I set it in a room, and so the temperature of the ambient room is 75 degrees Fahrenheit. Okay, so it's obviously going to cool down. All right, it's going to lose its heat. The temperature is going to decrease, eventually reaching 75 degrees. Now it will do that. If we start up here, it's at time 0 at 200 degrees. It'll go down to 75 degrees at some point, right? So it's going to be almost asymptotic, but at some point it will actually reach 75 degrees, okay? Or it'll be so close that the difference will be negligible. All right. And it's probably obvious, but I'm going to state it. If, for example, instead of putting this a cup of coffee at 200 degrees Fahrenheit on my kitchen table, where my kitchen is 75 degrees, if I took it outside and where it was, let's say, 35 degrees Fahrenheit, then the difference is greater, and so the rate at which it cools is going to be faster. It will cool down at a quicker rate because the difference is greater, right? And so that's what Newton discovered. So if we look at y equals y sub 0 e to the kt, the same sort of formula applies, except we're not looking at some values here. Instead, we're looking at the temperature of the object and the difference between the temperature of the object and the ambient temperature. Let's call it T subscript A, right? So the difference between the temperature of the object at the beginning, or at any moment actually, and the ambient temperature. And so that will be sort of like our Y. And then the initial will be the initial temperature minus the ambient temperature, e to the kt. All right, t being the time and k being our constant. So it's the time at some point minus the ambient, and then that's going to be like sort of the final, isn't the final temperature, but it's the final difference between the temperature and the ambient. So whatever, at some time in the future, the difference between what the temperature is and the ambient, that difference is what we're talking about here. This difference, right, the original initial temperature and ambient, that would be that difference. All right, does that make sense? So it's not temperatures we're putting in here, but the difference in the temperatures. Okay. Now you'll see when I reveal the formula here that we typically write this formula as T and then at some time. So instead of just T, we say the temperature at some time. So we think of that as the function, and that's equal to, we move the T ambient over to the other side. And so then it's T sub 0 minus T ambient e to the kt. Okay, so this is the formula that we use, but I just want to point out that the original sort of formula is, instead of y, we have the difference of the temperature and the ambient at any given time, and then the difference of the initial and the ambient at the beginning of whatever we're calling time 0. Okay. And so that's kind of where we get this formula from here. All right. So T of T, so that sounds a little confusing, but it's big T is the temperature, small t is the time. So that's the temperature at some time t, and it's like the function. The temperature is a function of time. T sub A, that's the ambient temperature. That's going to be assumed to be constant. T of 0, or we don't really write it as T of 0. What we'll write is of T with a subscript of 0. That'll be the initial temperature, okay, at time 0, whatever the time frame is at time 0. K will be the constant, and then T will be the time. Most of these it'll probably be minutes, but it could be seconds, it could be hours as well. All right, so let's read this first question. It's kind of a long, involved question, but let's read through it. All right, as part of his summer job at a restaurant, Jim learns to cook up a big pot of soup late at night just before closing time so that there would be plenty of soup to feed customers the next day. He also found out that while refrigeration was essential to preserve the soup overnight, the soup was too hot to be put directly into the fridge when it was ready. So he cooks the soup, the soup is ready, except we're not going to serve it today. We're going to put it in the refrigerator, cool it down, preserve it overnight, and then it will be ready to warm up and serve to customers tomorrow. The soup, assuming when the soup is ready, the soup had just boiled at 100 degrees Celsius. And the fridge was not powerful enough to accommodate a big pot of soup if it's any warmer than 20 degrees Fahrenheit, 20 degrees Celsius. All right, so you have this big pot of soup that's 100 degrees, but you don't want to take that boiling pot of soup and just immediately put it in the refrigerator. So you really want to let it cool down to 20 degrees Celsius. Then you can put it into the refrigerator, and the refrigerator will continue to cool it down overnight and preserve it until the next morning. All right, Jim discovers that by cooling the pot in a sink of cold water, so he puts the pot of hot soup into the sink, stopped up with cold water, and then he just lets the water run so that it stays kind of at a constant temperature, constant cold temperature, so that it's cooling down the soup. This is like if you're trying to cool hard-boiled eggs, right? So you cook hard-boiled eggs, you boil them, you take them out of the water. What do? You put them in a bowl of cold water, ice water, whatever, to cool the eggs down. So the same kind of thing. He's taking this pot of soup and putting it into a sink that's stopped up with cold water running into it, maintaining a constant temperature. So the water's kept running so that the temperature was roughly constant at 5 degrees Celsius. So it was fairly cold water that the pot of soup is sitting in. And then he's stirring it occasionally, that he could bring the temperature of the soup down to 60 degrees Celsius in 10 minutes. All right, so in 10 minutes he could reduce it. Now think about, draw a picture of what's going on here, right? So we have the soup finishes cooking. It's 100 degrees. Now we want to take it down to 20 degrees at some future point, right? At some point. We don't know what time that would be, but in 10 minutes, he's able to bring it down to 60 degrees. So we want to think about, okay, it's coming down and it's going to have a curve, right? So if we know 2 points, that's generally enough to figure out what we want, what we want to use it to find our K. All right, so how long before the closing time should he be ready so that Jim can put the soup into the fridge and then leave on time? So it's closing time. He doesn't want to have to sit there and babysit the soup and stay on the clock and get paid to sit there and stare at the soup while it cools. He wants to do that before closing time. It'll sit there, I don't know, 20, 30, 40 minutes, however long it takes. And then the soup will be cooled. It's closing time. He can put it in the refrigerator, and then he can leave on time. Okay, so that's kind of the situation. If we let it sit in the sink long enough, of course, it would eventually get down to this 5 degrees Celsius. So think of that as an asymptote that it's getting closer and closer to. All right, so I've put down some things for you here. So what is the ambient temperature of the water? That's 5 degrees Celsius. What is the initial temperature that's of the soup? That's 100 degrees Celsius. And then what's the temperature at time equals 10 minutes? That's 60 degrees Celsius. All right. So, fill out this form, stop the video and fill out everything for the formula, and then start up the video again and see if you did it correctly. So first thing we want to do is solve for K. All right, so we know the K, remember we're using 2 points that we know both the time and the temperature for to find our K. This point out here, when we reached our 20, we know the temperature, but we don't know the time at which that happened. So 2 points that we know both the time and the temperature. And so that temperature at time, so essentially at T equals 10 minutes, what's going on, right? At 10 minutes, the temperature is 60 degrees, ambient is 5, and I'm going to just keep putting this in square brackets. You could use parentheses, doesn't really matter. So that's the initial temperature minus the ambient temperature, and then e to the k, and then the time at which we're 60, well, that's just 10. Okay. So the first thing we want to do is really subtract this 5 from the other side, and then we'll divide by this 95 that's in the bracket, and so and then take the natural log of both sides to get this variable k down out of the exponent. So we have the natural log of 55 over the 95. And then that's equal to this 10k that comes down in front. Natural log of e, of course, that's 1, so we'll ignore that. So k will be equal to the natural log, again, that ratio, 55 over 95. Divide all that by 10. And so, and it makes sense, I think, because it's kind of approaching this asymptote. It's decreasing, right? The temperature started at 100. And it's going to approach 5 degrees if we let it sit in the cold water long enough. So what do we get? We get negative, and that makes sense that it's negative because it's decreasing. 0, 5, 4, 6, 5, 4, 3, 7, 0, 6. Again, science teachers would have a fit if we used all that decimal places, but we're sort of pretending that everything is exactly what we say here, although measurement errors would occur, of course, and we would never in science class use that many scientific places, decimal places. All right, so now we know our K. Now we want to concentrate on this point out here, right? We know the temperature. We're allowed to take that pot of soup and put it in the refrigerator if the temperature is down to 20 degrees. And so what time will that happen? That's what we're really looking for. All right, so but that's the point that we want to look at. So we say, all right, that temperature, temperature at that time, which we don't know, but we know the temperature, we just don't know the time at which it happens. That's 20. All right, and that's equal to 5 plus, and again, we can just, I'm going to go ahead and leave it as 100 minus 5, 100 minus 5 to emphasize that it's, this thing, but it's 95 if you want to write that in. E to the negative 0.0465 ... and then t. In this case, we know everything except the t. That's what we want to solve for. All right, we know the temperature at that time, but we just don't know what that time actually is. All right, so we'll subtract the 5 again, so that gives us 15, divide by the 95, and then take the natural log. We're taking, again, natural log because we have e, equals, bring all this down in front, negative 0.0465 ... t, and then to get our t, we simply divide by the k constant. So the natural log of 15 over 95, and then, you want to recall previous answer when you go to do that, right? So save this in here. You haven't touched your calculator yet, hopefully. This is the last thing you calculated. Now do natural log of 15 over 95, and then divide that answer by that value by the previous answer. And if you're able to do that without touching your calculator in between, you should get 33.7727. So we'd say about 34 minutes. So if he finishes the soup, cooking it 34 minutes before closing time, immediately puts it in the sink of cold water, then in 34 minutes, he should be able to decrease the temperature down to 20 degrees. And as a result, be able to put it in the refrigerator and leave work on time. All right, let's look at another one. Now, notice that our k here was negative. And it kind of makes sense. We're decreasing, so it should, just like we saw in growth and decay, for decay, it was negative. For growth, it was positive. So honestly, the very first time I looked at a problem like this, where we're putting a casserole in the oven, the casserole, let's just read through it. I put together a casserole, and it sits on my kitchen counter before I put it into the oven to cook. All right, so the temperature of the casserole is 75 degrees, because that's the temperature in my kitchen. So it's sitting on the counter. I assembled it from all these pieces that were 75 degrees. So the thing is sitting there, it's 75 degrees. I put the casserole in the oven at 5 p.m. and assume that it will cook in an oven whose temperature is a constant 350 degrees. All right, at 5:30, so 30 minutes later, the casserole temperature registers 120 degrees. At what time will the casserole temperature be 180? So I'm going to assume that 160. So when it reaches 160, it's warm enough, I can pull it out and eat dinner. Okay, so what's going on here? So when I first did this problem, I was expecting my K to be positive because the temperature is increasing. However, this is not exponential growth. Exponential growth, like when you put money into a savings account that grows exponentially, it goes up like this, and there's no upper bound. That would be exponential. In that case, K is positive. But what's happening here? This is acting very differently. We're putting this in an oven at 350 degrees. The thing starts at 75 degrees. Of course, the casserole will never reach 350 degrees. If it did, it would be burnt, right? I mean, it would be cremated. So if you think about, I don't know, if you're eating a steak, even though you might cook the steak in an oven, I don't know, you don't generally cook steaks in an oven, but let's just say you're going to take a steak and cook it in the oven. The oven's 350 degrees, but the steak is considered well done when it reaches 180 degrees. So, the casserole is not going to reach 350 degrees. It would be completely cremated if it was. So, but it's increasing. The temperature is increasing, but you can see over time it's getting closer and closer to this asymptote. So it's not like exponential growth like money in an account. It's still approaching an asymptote. So it's not growing like population growth and that kind of thing. Population growth doesn't reach a maximum and then kind of level off. It doesn't approach an asymptote. So in these cases, even though the temperature is going up, the casserole is getting warmer, we still have a K value that is less than 0 because we're approaching an asymptote. Either from above or from below, you're still going to see a negative K here. Okay, which was not intuitive when I first started thinking about this. When I first did these problems 15 years ago, I was, going through it blindly, and the K came out negative, and I was like, wait a minute, why is the K negative? The K should be positive. The temperature is increasing, but it's just increasing in a very different way. Okay, so what's the ambient temperature? That's 350 degrees. The initial temperature, that's 75 degrees. And then at some future time, we know. So we have the temperature at time 0, and then 30 minutes later, we have the temperature, and of course this isn't drawn to scale over here. We know that the temperature is 120. Okay, so then at what later time does the temperature reach a little bit more at 160? That's kind of the key. So what do we know? We know that at time 30 minutes, it's 120. How much time will it take for it to go up that little bit more from 120 to 160? That's what we're looking for. So what is the time needed for it to go from 75 up to 160 up here? All right, so plug that into your formula. So 120 plus is equal to the ambient, 350, plus the initial, 75, minus 350, e to the kt. Except t, we're trying to find the k here, right? So t is 30, because that's the time that this temperature is reached. So 30 minutes later. Okay, so you solve that for k, bring the 350 over, subtract it, divide by this, and then take the natural log, bring this stuff down in front. So same kind of thing. So we're going to get, when we subtract 350, we're going to get negative 230 divided by the difference of these is negative 275. So both negatives are going to cancel. That's fine. So our argument is going to be positive. So we take the natural log, and that's going to be equal to 30k. So let's just divide through by 30, and that should equal k. All right, so plug that all into your calculator. And again, it's negative, which at first, like I said, the first time I did these problems, 15 years ago, I was like, wait a minute, why is that negative? But it should be, because it's approaching an asymptote. Even though it's increasing, it's not increasing exponentially. Okay, so we've got that. Now we've got our k. So now we've got to find the time at which that casserole reaches 160 degrees. So we know our final temperature is 160. I don't know if I'm going to be able to fit that in there. Let me start over a little further. 160 equals the 350 plus the difference. Let's just put that in as negative 275 for sake of space here. And then e to the, I'm just going to say kt. We know the k, of course, right? That we have that down here. But so for space, I'm not writing it all in. All right, so the first thing we want to do is subtract the 350, divide by the 275, then take the natural log. So let's just do that. Natural log of the difference in these is negative 190, this negative 275, and that's equal to e to the kt. Now let's take the natural log. That'll be k times t. If we divide both sides by k, negative 0.005 ... and that should be equal to t. Okay, so we've done this enough times. Hopefully you're seeing this. I'm subtracting the 350, dividing by the 275, taking the natural log of both sides. That leaves me with kt divide both sides by k, and that should equal t. So plug all that into your calculator. Again, if you haven't touched your calculator since you did this calculation, you can recall that previous answer. Otherwise, plug all those in. And so this is 62.0756. And so that's roughly 62 minutes. So just about an hour of cooking time for that to reach your 160 degrees. So 62 minutes later. All right, let's look at the last problem. Temperature inside your house is 65 degrees Fahrenheit at 2 p.m. The outside temperature is 88 degrees Fahrenheit. Now assume you don't have your heat or air conditioning on in your house. Assume the outside temperature is constant, so that 88 is going to be constant all day long. At 5 p.m., the inside temperature has risen, so it's gotten a little bit warmer. At what temperature will the house be what temperature will the house be at 11 p.m.? All right, so what's happening is the ambient temperature outside, 88 degrees. That's our asymptote. The house is starting at time 0. We're saying at 2 p.m. 2 p.m. The house is at 65 degrees. Now we know at some time later, 3 hours later, at 5 p.m., the temperature is up to 68. Okay, and then we want to go, now this time we say at 11 p.m., what's the temperature? So we have again 2 points where we know both the time and the temperature. That's going to be enough to give us our K. And then we want to think about this point out here. In the last couple of problems, we didn't know the time, but we knew the temperature we're interested in. This time we know the time, but we don't know the temperature. Okay, so we're interested in knowing, okay, what is that temperature going to be? All right, so let's use those 2 points to find our K. I didn't write this stuff out, but it's not a bad idea to write that out again. So the ambient temperature, 88 degrees. The initial temperature at time 0, that's 65 degrees. The temperature, 3 hours later, so T of 3, that is at 68. Okay, so plug in everything you know to find your K. So 68 is equal to 88 plus 65 minus the initial minus the ambient. And then e to the K, the T would be 3 hours later. All right, so solve this one for K. Again, subtract the 88, divide by the negative 23 that we get here. Take the log of both sides, bring the 3K down in front. So we're going to get negative 20 when we bring the 88 over. Divide that by the negative 23, that's this. Take the natural log, and that will equal on this side 3K, divide by 3, and that gives us our K. All right, so let's do that down here. K then is equal to negative 0.0465873141. All right, so again, and it's negative with all this law of heating and cooling, the temperature, whether it's rising or whether it's decreasing, the temperature is decreasing up here or rising like these two were, you're still going to get a negative K value because we're approaching an asymptote. So the difference in the temperature and the ambient is decreasing as time goes on. So whether or not the temperature itself is increasing, it's really the difference in these temperatures is decreasing over time. And so that's the same up here. The difference in these temperatures is decreasing with time. The difference in the temperatures is decreasing with time. And so that's why really we have a negative. Okay, so now that we have our K, use that to find at 11 p.m., find the temperature. So we want the temperature, and so 11 from 2 p.m., 11 is 9 hours later, so that we want the temperature at time equals 9 hours, and that's 88 plus 65 minus 88. Again, we know that's 23 from over here. If you wanted to put that in, that's fine. And then that's e to the k. I'm doing the k bold here. We know what the k is, and we know what the t is, actually. That was 9. So the unknown is this thing over here this time, the final temperature. So this is pure calculator work. The K, we have that here, plug that in. And again, if you haven't touched your calculator since you calculated it, you can just, recall previous answer, right? And use the previous answer when you type in the K. So plug all that in. The time 9 hours later is 72.877. So we would say that the temperature, the temp at 11 p.m. is about 72.9 degrees, if we want to say Fahrenheit. Okay. All right, so that's this page. We're finished with this page now. That's the law, Newton's law of heating and cooling. This is your homework, and that homework is covering all the different types of exponential equations that we're solving for. All right, and that is due next class.